Thank you for that introduction. So as was mentioned, today I'm going to be not necessarily talking about connected vehicles or fleets, but we will be talking about how different agents can interact and hopefully give some hints about how we can do this in a safe way. So today, most of what I'll be talking about is fairly experimental, so a little bit more on the empirical side, but I think it gives some good insights to how these systems work in practice. The work I'll be presenting was primarily done by one of my new graduate students, Joe Huang, and in collaboration with Cheyenne Mitra, also at the University of Illinois, Urbana-Champaign. All right. So to give just a little bit of context and background for where I'm approaching this problem, my research group generally tries to answer this question. So how can we ensure safety in autonomous systems that have to operate out with people in the real world? So to answer this question, we generally look very closely at how humans behave. So thinking about how we can develop good models and come up with new methods to capture this behavior, often pulling from tools from learning and optimization to basically develop these models. Then we want to take these and combine them with this strong foundation in control, so we can actually think about how to deploy these systems and how to leverage these models for safe execution. Pretty much everything that we develop, we try to deploy if possible. So hopefully everything that we do in simulation or in theory is demonstrated in some sort of real world system or in practice. So there's a pretty strong experimental component there. And hopefully by developing these tools and doing this rigorous testing, when we go to actually deploy these systems at scale, we can get the sort of performance that we expect or that we see in the lab and make sure this matches when it's out in the wild. Okay, and so just as a little bit of a motivation, I think everyone has already seen this video at some point, but I really like to think about how people sort of are very, very good at interacting with other human agents. So this is this video of these human drivers seamlessly interacting at an unstructured intersection. So it's important to note here that when we look at just the drivers interacting, they're negotiating, they're interacting. And even though it might seem a little bit risky, this is all technically safe here. And perhaps another thing to note, let me get my laser pointer out here, is we do have many different types of agents here. So we have this sort of section here where we have these pedestrians that are, going out into the road, and again, seemingly high risk faction, but we still see, ultimately safe behaviors. So I think often when we think about safety in vehicles, we often think about perhaps closer to the center of this intersection, but today we'll be focusing a little bit on this part here. So again, I think these videos are sort of nice to give some motivation and motivate us to start capturing basically how humans nominally interact and see if we can recreate this interaction in our systems that we want to design and deploy. So normally when we think about safety, we often think about this from a control perspective. And often we cast this as something like a robust control problem. So if we were to think about the sort of classic formulation of this, we can basically say we want to safely and efficiently control some vehicle. So we want to find the controller that will basically guide the system that's governed by some dynamics F. And we basically want to say we want to safely control this vehicle, even in the presence of some uncertainty or some disturbances. So we often just capture this as some additional equation that can be both a function of some uncertainty as well as the states or the control itself. So this is sort of the classic formulation of robust control. And often when we want to think about formalizing safety and think about how to execute it, this is sort of the default formulation that we would think about. And this is a very well-studied problem. This has been around for a very long time. And this has been very good at capturing things that we can capture sort of with this additional function on the right side here. So this has been very good at taking into account things like sensor noise or environment uncertainty. So if we have some things that are unmodeled, this is very good, or these tools are very good at capturing these sorts of components. And this is sort of this side of the equation, and this is often how control theorists often think about the problem. So they want to capture this uncertainty and define the controller to be robust against this sort of uncertainties. As the learning community is also trying to look at decision-making and control, some other sides of the coin, like model mismatch, where we have some either unmodeled phenomenon, or perhaps we have a system that is optimized in simulation or on data, but has to be executed on a real vehicle. This sort of model mismatch is also getting a lot of traction. So often we're thinking about how we can develop robust policies or robust controllers that can take into account this mismatch in the real world. And again, sort of thinking about these two classes of problems, casting it in this sort of formulation tends to work pretty well in practice. And again, has been very well studied from both the control and the learning community. But as we start thinking about how these systems are deployed into this multi-agent environment, or when they start interacting with people, we have to sort of start thinking about how we can capture more long-term interactions. So while these sorts of methods often are a little bit more on the reaction side or reactive side, and tend to just think about one step or a few step safety and robustness, as we start thinking about interactions between different agents, we really need to start thinking about how we can capture these longer term interactions. And usually this doesn't necessarily fall directly into this robust control framework. So often what we do is we try and think about how we can specifically model these interactions, or think about how we can develop good predictive models that then we can design controllers around it. And looking at these sort of driver interactions or human driver modeling, and then those associated control frameworks has been a subject of many PhDs, theses, including my own. And there's been a ton of work basically looking at how to predict and understand these driver behaviors. So again, a ton of literature on looking at these driver interactions. But as I mentioned, what we want to try and do is think a little bit more about the pedestrian case. So this is sort of an important application because these pedestrians tend to be more vulnerable agents. While there is some flexibility in how bad a collision can be between vehicles, you don't really have this safety buffer with pedestrians. But as I mentioned, this idea or these concepts behind driver modeling have been very well studied in the past. So if we want to take these ideas and apply them to the pedestrian vehicle case, the first question you might ask is, can't we just apply these same tools or apply these same methods and use it in the vehicle pedestrian case? So this is our first question. Are these interactions any different, or can we just apply these tools and methods to this slightly different context? So my answer is sort of. There are some tools that can be applied or modeling tools that can be used for sort of any sort of human agents, but the pedestrian case is especially hard. And one of the first reasons is that simulations as well as data sets for these vehicle pedestrian interactions are not really readily available. So we have lots of tools for modeling or simulating driver behaviors. As this example here, this is just a simple loop using the intelligent driver model to basically model and recreate traffic. So this is a relatively simple tool, but we have lots of readily available systems, so we can model and start sort of playing with different approaches here. Similarly, there are tons of data sets out there on driving behaviors, which allows us to really develop a lot of models and predictive tools for such systems. So it really allows us to explore the driver case. However, if we start thinking about pedestrians, there are lots of crowd cases, but there really aren't the same sort of vehicle pedestrian interaction cases. Usually we have only a few examples because this isn't really a prevalent part of driving. So even if we don't have these systems available, we can also look at doing our own experiments. And one thing that we found is that even doing these experiments with vehicles and pedestrians are a bit of a production. So here, this is the one experiment we could get approval for. And you'll note right here, this is not an actual human. So often you have to think about some workarounds so you can still guarantee safety of your participants. So even if you're trying to do something totally in-house and show that the system is safe, it's often quite difficult to do just in person. We'll talk about some in-person experiments later though, but typically this is a bit of a challenge just because of the inherent safety risks. And just one last piece of motivation. Some of my work is on validation, so trying to see where these systems tend to fail. And one thing that we found is pedestrians are really, really challenging in these cases. So in this example here, I don't know if it's playing that well, but we have this case where the pedestrian tends to just sort of run straight into the car here. Or here at the bottom, we have this case where basically they are kind of stuck in this negotiation phase. But basically the key idea here is when we are actually going and testing these autonomous vehicles in the validation case, or trying to find these failure cases, we either have the case where the pedestrian models allow too much freedom, so it's too easy for these systems to fail, or we have the case where we just tend to find that this is sort of where the autonomous vehicles have a lack of understanding. So this tends to be a very sensitive point. So basically, in summary, this is sort of an important area because of the safety risks, but it's typically both hard from the technical perspective as well as the practical perspective as well. So today, we're going to basically talk about two different components. We'll likely only get to this first point. So we'll talk about some work we've been doing and trying to develop predictive models for pedestrian behavior. So we can design these safe vehicle pedestrian interactions. Alternatively, we can think about this as how can we design a system that can convince me to walk in front of a moving vehicle, which I know a little bit too much about. So we'll think about this case here, and depending on time, we might talk about some work on making inferences in the occluded pedestrian case, where we've done some other larger scale or more multi-agent experiments. Okay, so let's start with this point. So again, we want to basically think about how we can design a framework so we can have these safe vehicle pedestrian interactions. And first, we're going to start with coming up with predictive models, or a predictive model that we can then use for this downstream safety task. So if we want to think about the different classes of prediction methods, this typically takes the form of one of two methods. So first, we have this physics-based method. And the second is this pattern-based approach. So you can kind of think of this as a model-based approach or a data-driven technique here. So if we wanted to take a physics-based method, we basically try and model our system or our agents as other dynamical systems. So we have, again, some dynamical equation that will guide the motion of our agents that might be perturbed by some sort of noise. But basically, this is a sort of the classical formulation where basically we want to find this dynamical model that tends to match these human agents. So it's really nice if we can take advantage of these models or these approaches. So we can start, so we can really apply a lot of the tools from the sort of classic control and the classic safety techniques and apply them here. On the other hand, again, we have this pattern-based method. And typically when we take these data-driven or these pattern-based approaches, we tend to try and model this as like an n-step Markov process where we have some observation window, and we want to basically predict the next time step here. More generally, we basically say we take some window, we have some observations, and we want to predict our next step more directly. Often with the pattern-based methods, we don't just predict one step ahead, but we want to predict a full trajectory. So often this is a longer trajectory here, or a longer vector that captures this sort of some time horizon of predictions. And again, so these are often sort of two distinct methods. And one of the questions we want to start sort of hinting at is, are there ways we can combine these two methods in a nice intuitive way? So we can basically try and get the best of both worlds. Because again, with the physics-based methods, we tend to have a lot of nice tools and insight from the models themselves. But the pattern-based methods are typically better at capturing some of the nuances and the sort of real-world behaviors that we tend to see and observe in practice. And maybe to just highlight the importance of this problem, here's a quick reference. So this is a number of papers published over the different years. And as we can see, we're sort of seeing this like exponential growth in papers published in this area. So this is becoming a very hot topic and has a lot of sort of important and practical applications. One thing to note here is if we were to look at sort of these two different pieces, the physics-based methods have sort of petered out here, and these sort of learning-based or pattern-based approaches are really sort of taking charge for a lot of this. So again, this is sort of becoming a more and more popular area. And as maybe a quick aside, there are a few benchmarks that sort of try and benchmark and compare the different approaches. And the top method is one of these learning-based approaches. And we can see these are the final errors that they're getting. So this is displacement errors, and this should be in meters. And I think one important thing to note, again, this is more of an aside than anything else, but we see these learning-based approaches are getting sort of the best accuracy, but the physics-based approaches are not very far behind. So even though I think these communities often seem at odds, the net gains and the differences are often fairly small. Okay, so again, one of the things that we're going to try and do as we're presenting our proposed method for pedestrian prediction is how can we sort of combine the insights from these two different methods and approaches. So how can we take these insights from the model-based predictions, but still use the pattern-based or the learning-based approaches to try and get some of, or capture some of these human tendencies. So can we do something or develop some method that can help us get the best of both worlds? Okay, so one other thing that we would like to add to our prediction. So let's look at this example here. So if we're tracking this pedestrian, we're trying to predict where they will go. We can observe some prior behavior. And we can apply either method or any approach to basically try and predict where this vehicle will move in the future. But often if you have basically no context or no other information, you'll tend to just sort of get some average behavior, or this will sort of collapse into something like an expected forward motion. So often what we try and do is we try and add some other information, like the goals or intents of the agents. So then you can basically try and decide where they're going. And by taking into account this future behavior or this sort of high level abstraction, we can often get more informative and better predictions. So often we think of this as a goal-oriented prediction or something that is intention aware. And this is the method we're going to be trying building up for the rest of our talk here. So we can basically think of this as two separate problems. So the first problem is how to infer human intent. And the second is how to predict the future trajectory. And as a quick motivation for some intent, so often when we observe motion, or we as people observe motion, often we actually care very little about these surface behaviors. So as people are observing other agents or interacting, we don't actually know the physical state of the agent, but we often sort of care about these sort of higher level ideas like intentions. And it turns out from the, if we look at literature from the psychology or the cognitive sciences community, these intentions really determine how we understand, recall, react, and predict these human agents. And one thing that you might find, or that has been observed, is that when people are observing motions of other agents or other people, typically we tend to agree on where these sort of separating boundaries lie. So we often are able to identify these discrete actions corresponding to intent. So for a quick example, in the autonomous vehicle case, if we are observing this vehicle driving, we can basically watch this, and usually, or with pretty high degree of consensus, we can agree when this agent is going to switch from something like lane keeping to lane changing. And while there is some gray area, this is actually fairly separable. And again, tying this back to the motion prediction, we'll find that incorporating this intent or these goals can significantly improve predictions. So again, trying to capture this human insight can help us do better when we're trying to predict this motion, and hopefully in turn, we can use this to design better and safer systems. Okay, so first we want to try and figure out a way to infer this, the intent of these agents. So we present this framework, which will allow us to basically come up with an intention-aware prediction. And we're going to infer this intent using a particle filtering framework. So for the most part, this is not exactly a new idea here. This is a fairly standard particle filtering approach. But we have these particle filters, and we initialize them with different intents or some different goals. We use this to generate trajectories or predictions from these intents. So for now, we'll just assume that we have some model that can forward predict given the intent or goal of the agent. This is combined to come up with new particle weights, do the sampling, and we'll talk about this mutation bit in a bit. But basically, this is then used to update our inference on what the intent of the agent is. And then in turn, we can use this to, again, use this sort of what we're now considering a black box prediction and forward predict where the agent is going to go. So this is a fairly standard particle filtering approach. Again, the sort of new things here are how we're going to actually do the prediction given some goal. Since every particle is assigned a intent or a goal region, we can assume that this is given for their prediction. So we'll talk about that in the next step. But the other sort of interesting thing that we add here is this idea of mutation here. So one of the common problems that we observe is that humans don't always have a single goal or a single intent, or sometimes they will switch intents. So often we need to sort of bake in some liveness or some way to capture this changing behavior. And we do this with mutations. So there's always some probability that these agents will sort of change their goals or change their intents. So to just compare sort of how this behaves, again, if you just take a standard filtering approach, what you'll find is if you have some observations and you're trying to infer one of these three different goals, you'll kind of have the filter converge on a single intent. And even as there's a lot of evidence that the goal has changed, it becomes basically very hard to overcome this because you've basically forgotten all these particles since you converge quite fast. And there are some ways to counteract this, but with this mutation, you can easily handle this case where as you gather new information, because you never sort of totally eliminate the possibility that you could have the intent wrong, you tend to be unable to capture these changes. So with the addition of this mutation phenomenon, we can capture these sort of difficult scenarios that are often very difficult or sort of ignored by most prediction methods. And as one little side note, in this case here, we're looking at this sort of toy example where we have three very distinct goals here. And while we do typically have these discrete intents or goal regions, this can be sort of further discretized so you can get more fine predictions of the goals themselves. But we'll keep playing with this toy example for a little bit. So to just show how this will work in practice. So let's look at this case here. So again, this is the same example that we were looking at before, where first we initialize all of our intentions with something like equal probability. So you can see we can get some sort of weird samples or sort of off-looking trajectories later. But as we start gathering more information and coming up with a better inference, we can basically then see how this improves down the road. So as we run this, we can see we have a pretty solid prediction and seemingly reasonable trajectories that are sort of coming out of our observed trajectory or our observed pedestrian here. And at some point, when the pedestrian starts moving to its next goal, we can see that we are able to sort of capture this change in behavior. And we have a sort of pretty robust prediction in this case. Okay, so now let's assume, or hopefully I've convinced you that we have a pretty good way to infer the intent of the agents. So now let's think about how to actually generate these different predictions, which again will actually help us determine which intent is the more likely method in our filtering framework. Okay, so again, let's assume we have some observation sequence from the agent. We have our pedestrian or last observed position here, and we say, given some intent or some goal region, we want to figure out what the future trajectory is. And as I mentioned, if we were taking a physics-based approach or trying to do something from a more nominal modeling type approach, we can actually do a pretty good job of, capturing the end goal here and using this to determine our model. So first, we're going to use this nominal or physics-based model, and we're going to call this our nominal prediction. And to generate this first baseline prediction, we're going to use a potential field approach. And basically what this is going to do is this is basically going to take information from our environment and come up with a set of sources. And these sources are going to basically represent obstacles or boundaries in the environment. And this will basically generate some repulsive forces. We can have a set of sinks, and this will represent our goal location. So in this case, we have our goal here. So this is basically going to be this attractive force that our pedestrian is going to try to get to. So basically, by using this potential field approach, we can come up with this nice linear model. And there's been a lot of work in basically trying to get this state space model to capture and mimic pedestrian behavior. But basically, at the end of the day, this is going to give us a nice linear model here. Because in the examples that we'll look at here, the environment is pretty sparse. So more or less, this is basically going to give us a direct line or a straight line prediction to our goal place or goal position. But this can be extended to capture more interactions, and that's one of the nice things about the potential field approach. Okay, but as we can see in this example, if we look at this prediction and we see this nice straight line, we can probably guess that this isn't exactly how a human would actually move. So while this is sort of effectively capturing our goal, and is sort of nice to think about and model, it's not really capturing some of the nuanced behaviors or how people typically move. So we want to start seeing how we can augment this or generalize this to capture more of the typical tendencies of humans. So let's say we have our ground truth trajectory that is like this. So again, we have our social force model, or this linear model that takes into account this goal and basically allows us to go straight to the goal itself. We can also think about how if we were to just take this data and train some model, so take a pattern-based approach, like some LSTM, if we were to get this, we'd probably get some trajectory like this. So one of the things that we found is, although this, at a high level might look a little bit more like the ground truth projection or ground truth trajectory, it doesn't really capture this end goal very well. Because these learning-based models tend to have suffer from things like accumulating errors and don't really capture constraints very well. So even though it's reflecting the tendencies, it's not capturing these end goals. Okay, so what we are going to propose is to try and actually take advantage of this physics-based model and figure out how we can work this nominal trajectory to better match and capture these ground truth behaviors. Okay, so often when you think about a learning-based approach for trajectory prediction, you often have some observation window, and then you have your prediction forward. And one of the really common things to do is take a displacement approach. So instead of learning sort of these global trajectories out, you can kind of unify what you're trying to learn by just learning these displacements itself. So you're basically just going to be learning the sort of step-by-step displacements. And this often is a little bit easier to learn since you're basically unifying what your output is going to be. The downside is you often have to do this sort of sequential learning. So you basically have to pass your current displacement effort into the model again. So you can basically, or you tend to get this sort of cascading or compounding errors as you go through. So again, what we propose is instead of learning the displacement as is common, we're going to learn an offset. So we're going to feed in this nominal prediction as well. And we basically want to learn how this is going to be warped to this actual behavior that's observed. So there's a few things that are very nice about this. So first, this is actually fairly reminiscent of a traditional sort of physics-based approach where we have our model and then we have some additive noise. So what we're doing is we're basically just trying to figure out what this additional piece is going to be. The other thing that's very nice about this is we can actually do all this in parallel. So you tend to have suffer less from accumulating error, and you have some faster computation speed as well. So again, we're basically trying to learn this offset. So you can kind of think of this as trying to take this nominal prediction and push it towards capturing these human tendencies. And there's a few things that are really nice about this. So first, this is actually very similar to residual learning. So we can actually use residual neural networks to try and capture these offsets. And you get a lot of the advantages or some of the sort of key insights that you get with these residual networks as well. So in particular, these sorts of methods, because you are basically just learning this additive component, so you're not learning basically this whole sum together, you're just learning this one piece. You tend to get learned outputs that are more stable. And you have this sort of nice property where you tend to not be worse than your nominal trajectory. So at least in training, and if your test environment is fairly similar to your training environment, you typically do not actually do worse and you only see improvement over this nominal trajectory. And another thing that's sort of another key thing that we did here was when we're adding this nominal trajectory in, we concatenate our observations with our nominal trajectory. So we have this vector of sort of two components. And by combining this whole trajectory or not distinctly separating the observation and prediction period, we can actually use these bidirectional methods. So basically what this is doing is in the internal workings of our network, it's taking these hidden layers and propagating them both forward and back. So we actually get a smoother, more continuous trajectory out. So it's just sort of a nice empirical observation that we have. Okay, so again, we want to basically put this into our full intention-aware prediction. So now we have our prediction method that says, given some goal, we take our nominal prediction, warp it a bit to capture these human tendencies, and we use this to update our intention, which can then be in turn used to produce a final prediction that gives us the trajectory from our current observation to our goal. Okay, so I'm going to go a little bit fast through this since I'm running a little bit low on time. But in short, this method tends to work very well. So we tend to have much better, we tend to capture these human tendencies. So most importantly, capturing these curvatures and non-abrupt movements that is often a little bit more difficult for some of these physics-based approaches. And one of the nice things that we get out of this is by simultaneously predicting or estimating the intent along with the prediction, we often get the sort of bonus utility. So in most of the sort of state-of-the-art prediction methods, they tend to predict trajectories or sort of produce a distribution over trajectories, but they don't actually provide a good way to help you select what the most likely trajectory is, and you basically can only use the mean. And often the metrics for this is usually the minimum error performance, but you don't actually have a good way to get that out of the data since you just have sampled trajectories. But given this framework, we can both isolate different modes of intent and have a nice way to basically get the average behavior out. Okay, so this is basically our prediction method. But as was mentioned at the beginning, we basically want to get this to the point where we can actually put it into the loop and have a sort of safe pedestrian vehicle interactions. So now let's talk about our framework for these interactions. So in some of our recent work, again, this is in collaboration with Cheyenne Mitra, we've been basically building up our autonomous stack so we can have these sort of nice formal guarantees to ensure safe interaction between these vehicles and pedestrians. So we're looking at a simplified case here where we have a single pedestrian with different goals. So first goal is to cross the road. The second would be to go alongside of our road, and then have our vehicle agent here that is basically moving along this path or the road. So we want to build up our full autonomous stack so we can basically take advantage of our built-in sensors and perception stack and bake in this intent estimation as well as trajectory prediction. So we can basically use this to get some guarantees in terms of the behavior and the interactions that we see here. So we're using this test vehicle. So this is a smart car that was provided by Autonomous Stuff that basically provides us this whole platform with the full sensor suite and everything that we can use to actually execute and test this maneuver. So as we talked about for the most part today, we have this pedestrian intent estimation here. So we can use this to generate or propagate trajectories out. So we can basically have a pretty solid prediction of where the pedestrian is going to go. We then want to pass this down into some reachability analysis tool so we can determine how likely a collision is and determine what the safe action is going to be. Then again, we want to pass this to the low-level controller and make sure we can execute our control as anticipated. So to quickly talk about this reachability framework, so we were using an online reachability framework with DryVR. Again, this is from Cheyenne Mitra's group. But the basic idea for this is we want to compute this reachable set. So we have some system A over some state space X. We have some modes of operation. In this case, we were basically just assuming that we had two modes of operation, which is continuing down or this emergency maneuver. We also have our set of initial states, and we have some look ahead time t. In this case, we're computing or we're approximating our real system with a 5-state bicycle model, which is a simplified model, but we'll validate that in a moment. But this basically provides us with our system dynamics of just the vehicle itself. So the way this tool produces the reachable set is it uses a sensitivity function. And basically what this does is it's able to bound the distance between sampled trajectories. And this is something that is pre-computed offline. So this sensitivity function is basically going to bound this distance with some ball. We take our initial set, and this is going to be partitioned into different regions. And from these different regions, we can basically propagate trajectories out of these different sets using representative states. And this will basically give us our sort of sample-based reachable set over some time horizon. But using this sensitivity function, we can actually bloat basically this sampled trajectories out so we can get an over approximation of the reachable set by basically looking at the union of this. And even though we're looking at a sort of simplified model of the vehicle here, what we find is we still get pretty high accuracy in terms of capturing the vehicle's performance. So we looked at different confidence levels. So basically what these different confidence levels are doing is looking at the different sizes of our initial set. So this can help us capture basically how much uncertainty we're assuming is in our system. So depending on basically how confident we are in both our perception and state estimation, we can basically expand or grow this initial set, and we get these sort of multicolored or expanding reachable sets that can capture this behavior. And as we increase our time horizon, we tend to get decaying performance, but as you can see, this is pretty effectively capturing this vehicle performance. And another thing to note is since we do some pre-computations offline and it is a sampling-based performance, we tend to have pretty good computation time for even pretty long time horizons. So we're basically able to get this online monitoring approach working pretty well. Okay, so now we have this tool. So we have our prediction, we have our reachability module. And again, what we want to do is close the loop on all this. So assuming that we have this good prediction, we can actually take this as a series of static obstacles. So then we can close the loop on this reachable set and effectively basically determine whether or not we should stop here. So by combining these two pieces together, at least I feel safe enough walking in front of this car. And I know I'm at time, but as a quick aside, there are a number of challenges and things that were not necessarily easy for us to do. So the first challenge was, so we're primarily working on this prediction and control component, but one of the big challenges that we had was the perception, and I'll actually circle back on this in a moment. And the other sort of open challenge I would say is that most of these reachability tools or even just decision-making control, often when you're incorporating these predictions, you often have a single or most likely trajectory. Or alternatively, you just assume you have something like the worst case. But we're kind of throwing out a lot of the insights that we have from having this sort of multimodal predictions or these alternative intents. And one of the other things is that we have this example with sort of this very few agents, but scaling this up is often very difficult. And so as circling back to this first challenge and maybe just as a bonus for you, so I'm not accused of cherry picking, here's a case where our perception system did not work and we had a sort of high risk scenario here where the car sort of came up and did not effectively stop. Okay. So often one of the problems that we had is it was difficult to incorporate some of the errors that we had from the perception actually in the framework itself. Okay, and since I'm at time, I will actually end here. So let me sort of scoot forward to my acknowledgements here. So I'd like to thank all of my collaborators for their help and the sponsors for providing both funding and the systems itself. And with that, I will take questions. So thank you for listening.